Chapter 19, Temperature. Now, what is temperature? And we heard about many times, and also we know how to measure temperature by using thermometer. As a matter of fact, temperature as the property that determines whether an object is in thermal equilibrium with other objects. Say, for example, if we want a cup of warm water, we need to put the thermometer into the warm water and wait for a while and until the thermometer reached so-called thermal equilibrium with the warm water. And then this thermometer will indicate the temperature of the warm water. Now, in order to clearly understand what is temperature and what is thermal equilibrium, let's first define thermal contact. Thermal contact defined as two objects are placed in an insulated container such that they interact with each other but not with the environment. So we can imagine that if we have object A and object B, and if we put them into an insulated box, that they were going to interact with each other but not with the environment. That is called thermal contact. Now be careful about this word contact. Well, contact doesn't need to be physically contact, because actually object A and B will be able to have thermal contact through, for example, electromagnetic radiation, and heat can be delivered through electromagnetic waves. So this is also kind of contact. That is action at distance contact. So right now the definition is as long as A and B are insulated from the environment and they're in thermal contact. Now second, we have to understand what is called thermal equilibrium. Thermal equilibrium is a situation in which two objects would not exchange energy by heat or electromagnetic radiation if they were placed in a thermal contact. For example, if we place object A and B in the insulated box and they are in thermal contact, and initially if A and B start to exchange energy, and but until to a point there's no more change of energy between A and B, then we say they are at thermal equilibrium. Well, that actually means they're at the same temperature, because no more exchange of energy means they're equal at a certain potential. So in that case, that physical property is what we call temperature. Now, the next one is Zero's law. It is very interesting because actually the thermodynamics first law was that's about conservation of energy, was defined first. Then later people thought there must be something else to define about the temperature, so they think that's more essential. They create the so-called Zero's law right here. The Zero's law says if object A and B are separately in thermal equilibrium with a third object C, then A and B are in thermal equilibrium with each other. That is a very interesting case. Say, for example, A and B, if A and B are separately in thermal equilibrium with C, for example, if A and C are in thermal equilibrium, that means there's no more change of energy and they reached certain kind of, let's say, same temperature. And then B, if with the same C, also reached the thermal equilibrium, and then we say A and B are also in thermal equilibrium. So which means if A and C have the same temperature and B and C have the same temperature, then A and B have the same temperature. That is very obvious. It's a little bit funny. Anyway, this is called the Zero's law of thermodynamics. Now, so we start to define thermal contact, thermal equilibrium, and Zero's law of thermodynamics. Next, let's talk about temperature. A lot of time we ask ourselves what is temperature, people will immediately think about hot and cold. Well, if temperature is high, well, which measured by thermometer, we say it must be hot. That is true. If temperature is low and we say it must be cold, that is also true. But reverse, it's different. It's not always true. For example, if we say, I feel hot, the temperature must be high. I feel cold, temperature must be low. That is not true. For example, here is a very interesting experiment that if I have 3 pots of water, one is cold water, one is hot water, one is warm water. Can you imagine if I put my left hand in the cold water and my left hand will say, well, it's cold. I put my right hand in the hot water and my right hand tells me, well, it's hot. Then, guess what? If I pull my right hand out of hot water, put into warm, I will say, well, this is kind of cold. But my left hand that is out of the cold water get into the warm water, and I will feel, wow, this is kind of hot. So my left hand tells me this is hot. My right hand tells me this is cold. So you see, if we try to determine the temperature of warm water, that my 2 hands cannot agree with each other. So we cannot determine the temperature by our human feeling. We must use something more scientific. That is something that we give a name called thermometer. Now, what is a thermometer? Thermometers are devices that are used to measure the temperature of a system. All thermometers are based on principle that some physical property of a system changes as the system temperature change. For example, say as a matter of fact, we know thermometer. The common one is the glass tube filled with liquid mercury or alcohol. And as we submerge this thermometer into an environment, for example, hot water, the mercury or alcohol will expand into a glass capillary tube. And by judging the height of this liquid mercury column or alcohol column, we can read from the thermometer about its temperature. So there's various kind of thermometer, and let's take a look at a very common one first. We must measure temperature by using the property of a certain kind of material. For example, that the glass mercury thermometer, we use the thermal expansion property of the mercury. Here we have a so-called constant volume gas thermometer. Now, this one is a bath or environment to be measured. For example, this is a cup holding the ice water. And this is a flask filled with gas. And the gas is everywhere filling here. And column A is connected with that reservoir B. And the purple color means that is filled with mercury. The reason we use mercury is because at room temperature, plus minus, I guess, 20 degrees, the mercury is a liquid. And liquid flows, so it makes life much easier. Second, that the mercury has very high density. Therefore, if you remember what we learned from the previous chapter about the pressure underneath the liquid, and a little rise of a mercury column actually gives a lot of pressure. So it will be easier for us to measure the pressure of gas. Now imagine that if we raise or lower the reservoir B until the level of column A line up with this scale at 0. And this moment, because the bath is filled with ice water mixture, we define that is 0 degrees Celsius right here. So at this moment, we will be able to know the pressure of the gas, because the pressure of the gas right now, if we pick a point here, that exposed to the gas, that carries the information about the pressure of the gas. On the other hand, this is the U-tube, the liquid mercury is connected. So at the same horizontal level, the other point right here has the same pressure as if we name this as point of 1, and that is point of 2. Point 1 and 2 have the same pressure because they're at the same horizontal level and the mercury is connected. So if we look at the pressure at point 2, if this one is exposed to the atmosphere pressure, that is P0, which is 1 atm, and the pressure at point 2, as we learned from the previous case, that P2 will equal to surface pressure plus rho, which is the mercury, and G and H. H is the height that the mercury column above point 2. So from there, we can calculate pressure at point 2. That equals the pressure at point 1. That is the gas pressure. So therefore, we got the information of at 0 degrees Celsius, that's what we define the ice-water mixture, and we get the value for pressure. And later, let's imagine if we replace this bath by steam and hot water mixture. That is the point we define as 100 degrees Celsius. So we define 100 degrees Celsius, and we use the same method to measure the pressure at point 2. This time again, we need to raise or lower the mercury reservoir of B until we reach the level of 0.1 reached at 0 of scale, and then we get this another different height. So the height is different, we'll get different pressure. Therefore, right now, look, the pressure is different because if you look at from the P scale, right now the pressure is higher. So now we obtain 2 points that give us a reference curve, which means in the future, for example, if I replace this bath by any warm water, but I don't know how many degrees Celsius is that, then I use the same technique until that 1 and 2 line up, I get a new height, which is called H prime prime. For example, by using this equation that I use H prime prime to calculate the pressure of P2 prime prime, and then say, for example, right now the pressure is this much. So I can go to the curve and say, now the pressure is this much, and I want to know what is the temperature of that warm water. So we can, from the scale, if we make it linear, we can find what is the temperature of that warm water. So this is a very original thermometer. It's called constant volume gas thermometer. The picture of the constant volume gas thermometer is on page of 580 for your textbook, and figure 19.3 is this one, figure 19.4 is the other one. Now let's look at something very interesting, that there are 3 different curves which we say will look like straight line, blue one, red one, and green one, and named trial 1, trial 2, trial 3. As a matter of fact, if you remember that constant volume gas thermometer, that we can use different gas, we can fill different gases in the flask. So actually trial 1 we use, let's say, gas number 1, trial 2 we use gas, the other gas, another kind of gas number 2, and trial 3. So we conduct a similar experiment to try to get the pressure versus temperature curve. It comes out a straight line. Now something interesting. For first trial, we find that 2 points. At 0, that is the ice-water mixture points, we find the pressure. And then 100, we find another point, that is the steam point, that we connect these two, we get that blue one. Choose another gas, we do the same experiment at 0 degrees for ice point, 100 degrees for steam point, and get red one. And the third one is the green one. If we extend this blue and red and green straight line, it is very interesting. They all end at a negative 273.15. At this point, that obviously is in Celsius scale, And what is Celsius scale? Well, we define ice point, ice-water mixture when the system exposed to atmosphere at 0 degrees Celsius, and boil water with steam mixture exposed to the atmosphere as 100 degrees Celsius. And then in between we will mark them linearly. That system called Celsius system. Well, on the Celsius scale, that all three trials end up at negative 273.15. At that point, pressure equal to 0. Well, which means the gas is not gas anymore, obviously, because the pressure, later you will learn, actually comes from the gas molecule moving around, hitting the wall of the container. So right now pressure is 0. That means they're all liquefied. So this indicating something very interesting. We decide to choose this temperature as a absolute 0. Absolute 0 temperatures are at which various physical processes occur. So anyway, let's look at the absolute temperature scale. Right now, we have another picture next to it. It has a new symbol which is called K. This K actually is the absolute 0 temperature scale. That K is representing Kelvin. And they give us some reference of, at that scale, hydrogen of the bomb has a temperature of 10 to the 8, that's 100 million Kelvin. Interior of the sun is around 10 to the 7, which is 10 million degree of K, and so far so forth. The surface of the sun is around 5 to 6,000 degree of K. And the lowest temperature achieved is 10 to the negative 7 K, which is very, very close to 0. So now, let's take a look at it. Exactly what is this absolute temperature scale and what is a Kelvin? The absolute temperature scale, we name it Kelvin scale. And how do we define it? And that is when Celsius is 0 degrees, and we say the Kelvin is 273.15 of K. Or if we have 0 degrees of Kelvin, and then the Celsius reaches negative 273.15. So this is that at that point all the pressure versus temperature curve for the gas reached pressure equal to 0. So therefore we pick that unique point at negative 273.15 as 0 degrees of Kelvin. Therefore, for the Celsius, if from negative 273 increased to 0, so it actually jumped by 273.15 degrees, then the Kelvin also jumped the same amount. So here's something very interesting, that is the change in delta T in Celsius exactly equals to the delta T in the Kelvin degree. The increment are exactly the same. They just have different starting point. Celsius start from negative 273, Kelvin say 0. If Celsius increase 1, Kelvin increase also by 1. So when Celsius increased by 273.15, Kelvin also increased by 273.15. So this is a very interesting relationship. Now, in order to define a temperature scale, then we need 2 points. If you remember Celsius, for the Celsius temperature scale, pressure versus temperature, and we choose 2 points. One is at 0 degrees Celsius, which is ice point. The other is the steam point, which is 100 degrees Celsius, and we have a straight line. This is the reference line. So once you have 2 points, you have this reference line, and we can define any other temperature. So this is a 100 degree of Celsius, and that is 0 degrees. So for the absolute temperature scale or Kelvin scale, which 2 points do we choose to make our reference curve? Well, the number 1 point is the absolute zero. That is at negative 273.15 degrees Celsius. The number 2 point that we choose is the so-called triple point of water. And that is at 0.01 degree of Celsius, while the pressure of the system is 4.58 of millimeter mercury high. What does that mean? Well, we can do the calculation about this much, which is density of the mercury, rho GH. So if you plug in SI unit, density of the mercury is 13.6, 10 to the 3 SI unit, and G 9.79 SI unit. H, you have to convert 4.58 mm to meter, which is times 10 to the negative 3. So you can calculate how much is the pressure. Because whenever you talk about temperature, you have to define at what pressure the system is exposed to. So the first point is absolute zero. The second point is triple point of water. Now, by the way, what is the triple point of water? It is a single combination of temperature and pressure at which liquid, water, gases, and ice coexist in equilibrium, which means we have liquid water, solid water is ice, and also we have gas, which is the vapor. The percentage of these three different, they have different phases, remain constant. This is called the triple point of water. So this happened at a temperature 0.01 degrees Celsius. At pressure to the system is 4.58 mm mercury high. So we choose these 2 points to make a reference curve for the absolute temperature scale. Now, so from that definition, that what is a 1 Kelvin degree? That 1 Kelvin degree defined as to be 1 of 273.16. Why is 0.16? Because the triple point is 0.01 degrees Celsius. That is above the absolute zero. So it's 273.16. 1 Kelvin degree is defined to be 1 of 273.16 of the difference between absolute zero and the temperature of triple point of water. So anyway, for us, what's most important is we understand the definition of the Kelvin scale. Where does it come from? That has come from a profound property, which is all the gas will reach pressure to zero at that particular point. That is a very unique. That's why we choose this as a reference point and create a new scale. Second, we need to know the relationship between Celsius and Fahrenheit that we know before. If you want to convert Celsius to Fahrenheit, this is the equation that you use. And if you want to convert backwards, obviously you plug in the Fahrenheit and you can convert to Celsius. Oh, by the way, how did people define a Fahrenheit scale? Well, when a system of ice water mixture exposed to air pressure, and we define this ice point as 32 degrees Fahrenheit. At that time, Celsius defined as 0. For the boiling water and steam mixture, Celsius defined as 100 degrees Celsius, and Fahrenheit actually defined as 212 degrees Fahrenheit. So they have a different number defined for the same ice point and steam point. Therefore, we can figure out a conversion between Celsius and Fahrenheit. The second equation is between the Kelvin and Celsius. It tells us that if you know the Kelvin temperature, if you know the Celsius temperature, say 0, and Kelvin is 273.15. So if you say 20 degrees Celsius, then it will end up 293.15 for the Kelvin. So that's the conversion between Celsius and Kelvin degree. That is the absolute temperature scale. And also, if we think about the change, if we delta this equation, the temperature for Kelvin equals the delta for temperature for Celsius, which means the increment are the same. But it's different compared to the Fahrenheit, because if we convert this equation and have this temperature in Celsius, for example, what we can do is this. Both sides of the equation times by 5 divided by 9. So, which means if you have Fahrenheit, temperature in Fahrenheit, what you do is you minus 32 first. Then we time of 5, we divide by a 9, and then that's how we convert to Celsius temperature. So, if you look at this equation, if we delta both sides, then delta T in Celsius equals to this coefficient will remain. The delta gets in, that is the temperature in Fahrenheit, and the delta of constant is gone. So, 1 degree change in Celsius, that is 1/5/9 of degree change in Fahrenheit. This is how we get that. So the increment is different compared to the Celsius and Fahrenheit, but Kelvin and Celsius are the same.